Welcome back to the lectures in quantum chemistry and molecular spectroscopy. We had in the last lecture looked at the microwave spectrum of a diatomic molecule as a rigid diatomic molecule. We shall continue a little bit on that, and in this lecture I shall also give some details on polyatomic molecules which are of specific types, namely a symmetric top polyatomic molecule, because the spectra of a symmetric top and the spectra of diatomic molecules are very similar, and some additional features are there for the polyatomic molecules. This is the last of the teaching learning modules for this particular course, and therefore I would summarize the microwave aspects as quickly as possible. If you recall the previous lecture, we left at a point when we were looking at the intensities of the diatomic molecular microwave spectrum and the ratio of the number of molecules in a given energy state to the excited to the ground state, or the ground state to the excited. Here it is a ground state to the excited state. If you look at that initial and final state, this ratio is given by the ratio of the degeneracies of the corresponding states multiplied by a Boltzmann factor which contains the energy difference between those two states divided by the Boltzmann factor kBT at a given temperature T. And we also know that the energy for a given quantum number J double prime is given by this value HCB times J into J plus 1. So, how do we look at the intensities? Now, the Nj, if you double prime, if you look at, is proportional to, that is a constant, is proportional to 2J double prime plus 1, which is the degeneracy for the number of states with the same energy, and an exponential minus HCBJ double prime J into J plus 1. Divided by kBT. Therefore, when we say that the intensities are tending to a maximum as J double prime goes from 0, 1, 2 to some value, what is that value J double prime maximum for which the intensity is maximum, and then it comes down. This is particularly the case for rotational spectrum because of the degeneracy factor that we have. Okay. In the case of harmonic oscillator in one dimension, the degeneracy of each harmonic oscillator state is 1, it is not degenerate. Therefore, this factor did not come in. Besides, the exponential factor for the harmonic oscillator contained the harmonic oscillator energy here, and that energy would be much greater. For example, if you write to the harmonic oscillator energy for the vibrational states, it would be minus h bar omega times n plus a half divided by kBT to determine the number of molecules in the quantum state n is proportional to that, because the nu n, the degeneracy, is 1 for a simple harmonic oscillator, and this factor h bar omega n plus a half is much greater than kBT. Therefore, n of n is very, very small except for the absolutely the lowest energy state, namely n equal to 0 state. So, we do not have a problem of a maximizing intensity of the harmonic oscillator for different vibrational levels. The lowest energy level transition from 0 to 1 has the highest intensity. In the case of rotational spectrum, there is a distribution, and the distribution looks pretty much like, if you put the intensities on one axis and the quantum number J double prime on the axis, you know that these are discrete numbers, so they go something like that. So, the intensity of transition for a given J double prime to the next one. This is another one and this is the other, this is the other. We saw the inverse of this because that was the emission spectrum. This is the absorption spectrum, this is what we see. These are the 2Bs and the intensities go through M maximum. Because this energy HCBJ, J into J plus 1 is much less than KBT, let us take the J to be continuous, and if you want to look at the number of J double prime, which is proportional, the intensity is proportional to the number, then what you need to do is to take this derivative d n J double prime as a function of J double prime. Approximately, if you set this equal to 0, then you get an extremum for this function. Please remember, this is approximate. After all, J is a continuous, is not a continuous number, J is a discrete quantum number. Therefore, when we say we are basically taking the derivatives, in a sense differentials, to be 0, it is an approximate procedure, and that is easy to immediately calculate for this process, namely if Nj double prime is nu J double prime, which is sorry, this is 2J plus 1, 2J double prime plus 1 exponential minus HC Bj, B not Bj, B, J double prime into J double prime plus 1 divided by KBT, then the derivative of this with respect to the quantum number J double prime is that it is a product of two functions. Therefore, there are two terms e to the minus HC B J double prime into J double prime plus 1 by KBT, and the other is the derivative of this, which gives you minus 2J double prime plus 1 times HC B, and this is the derivative of that is 2J double prime plus 1 by KBT times the exponential itself, J double prime plus 1 by KBT. And if you set this approximately equal to 0, you get a value for J double prime, and that is easy to write down. It is square root of, I think let's write that down. It's 1 by 2 square root of by HCB minus 1/2. So what it means is that for the value J double prime satisfied by this condition, the intensity is maximum. For all other J double prime, the intensity is on either side of the maximum, so it is lower. This is with the rotational spectroscopy. Therefore, we look at line positions given by the energies Ej as HC Bj into J plus 1 and the line intensities given by 2J plus 1 times e to the minus HCBJ into J plus 1 over KBT. So, we have looked at both of these for the diatomic molecules, and we have looked at some spectra. In summary, the moment of inertia I, which is given as mu r square, okay, is the one with which, and with the knowledge of B, we can calculate R, the bond distance. Therefore, it is a very, very accurate technique for calculating the bond distance to very precise values. Okay. So, let us move on to the next case of a polyatomic molecule. And for a polyatomic molecule, if it is an arbitrary molecule, let us see if I have those things mentioned in my lecture notes. So, we have something here the moments of inertia for polyatomic molecules. If we look at the details, then for a polyatomic system you have moments of inertia is not a very simple quantity, it is not a scalar quantity like what we did. Actually, for a general polyatomic molecule, the moment of inertia is a second rank tensor. I is in general a second rank tensor. Okay. A vector is a first rank tensor and in 3 dimensions has 3 components behaving in a certain way. A scalar is a 0 rank tensor, has only one component, namely the magnitude, and tensors are generalizations of the number of independent components in different directions. So, a second rank tensor has 3 raised to 2, you can call vector as a 3 raised to 1 and the scalar as a 3 raised to 0 in 3 dimensions. That is the x, y, z coordinate system that we use. So, in that sense the moment of inertia is a second rank tensor, but the physical requirement of the moment of inertia is such that when we write the 9 components in the form of a matrix with the 9 directions x, 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 y and I, x, z, I, y, x, it turns out that the x, y and y, x are the same, y, y and I, y, z, and likewise x, z and z, x turn out to be the same. This is the same as y, z and you have I, z, z. So, you have essentially 3 diagonal components and 3 off diagonal components of the moments of inertia, but the mathematics of the rigid body system suggests that we can in principle determine what is known as an axis system called the principal axis system, in which there are only 3 moments of inertia. I in the principal axis system, if you have to write, will have only 3 components, namely I, x, x. So, let me write that using a different coordinate frame. I, x, x, I, y, y, I, z, z, and all the off diagonal components are 0. And in this principal axis system, the rotational kinetic energy of a polyatomic molecule is given by the angular momentum about those axes j x square by 2 I x x plus j y square, the component of the angular momentum about the y axis, the principal axis, 2 I y y, and j z square by 2 I z z. So, this is the rotational kinetic energy in a classical form for a rigid rotor, in which the molecule has 3 different mutually perpendicular axis, and therefore, obviously this is not a linear molecule because all the 3 moments of inertia are non-zero and non-trivial. Okay. Therefore, we have a molecule in which all the 3 moments of inertia are different. We call this as asymmetric top. There is no symmetry for the moments, it is known as an asymmetric top. Top is a rotor like the normal top that you have. However, if 2 moments of inertia are equal but unequal to the third, this is known as a symmetric top. If all the 3 moments of inertia are equal in a molecule and non-zero, then this is called spherical top. Then in the symmetric top there are two classes, obviously depending on whether the equal moments of inertia or greater than the unequal moment of inertia or less than the unequal moments of inertia. You have two types, prolate symmetric top or an oblate symmetric top. And there are quite a few examples in the lecture notes that I have given in the course where some of these things are mentioned. We will concern ourselves only with the symmetric top molecule for the rest of 10-15 minutes and look at the spectrum of this molecule, and from that we have certain things to learn, and so let me get quickly to the details of that. So those things are explained in the lecture notes here with specific examples, you can see that. And for example, a molecule such as methyl iodide, in which the three axes, the principal axes are shown to you. The z axis is the Ci bond axis and the x and y axis are in a plane perpendicular to the Ci axis, and the center of mass is somewhere here. Iodine is a very heavy atom and the remaining CH3 are such that the center of mass is somewhere here. Therefore, you have the z axis, the principal axis this way, the x axis perpendicular to that in a plane, and y axis also perpendicular to both of these in the same plane. The x, y moments of inertia can be calculated to be the same and they are different from the z axis, and this is an example of a symmetric top. Another example of a symmetric top is the benzene molecule, in which the center of mass is right at the center of the benzene ring, and then you can see the three axis systems x, y, z, and you would notice that the moment of inertia about the x axis and the y axis are the same, but they are different from the third, the z axis moments of inertia. On the other hand, if you take the sulfur hexafluoride as an example, which has a perfect sort of an octahedral structure, you will notice that all three directions are identical and therefore all the three moments of inertia are identical. And this happens for a tetrahedral structure as well. Methane, all the three moments of inertia of the methane are identical. Methane is also a spherical top. Octahedral structures are spherical tops. So spherical tops have only one moment of inertia. Therefore, extracting information from microwave spectroscopy becomes more and more difficult when you have less and less variables. Water molecule, if you take, the center of mass of the water molecule is somewhere along the bond, the divider between the HO-H bond angle along that and right close to the oxygen atom, and therefore you can see that the three mutual principal axes that you have here are x, y and z, and you can calculate the moments of inertia and find out that all three are different. Therefore, water, ozone and simple triatomic molecules, sulfur dioxide and others are all asymmetric tops. Now, the energy level for a symmetric top follows very closely the energy level description of a linear molecule. So, if we have to write the Hamiltonian for a symmetric top, we have h bar square by 2 j x square by I x x plus j y square by I x x, because both are equal, y y and x x. Then you have j z square by I z z, and so you can write this immediately as h bar square by 2 into 1 by I x x j x square plus j y square plus 1 by I z z j z square. Please remember, these are all operators in quantum mechanics now, angular momentum operator, square of them, and therefore they have very specific commutation properties. And so what you see here is that the Hamiltonian written in the form of 1 by I x x times the overall angular momentum j square minus j z square plus 1 by I z z j z square, and therefore if we rewrite this, we have h bar square by 2, you have, we call this as b I squared plus a minus b I z square. Okay. So, what is B here? B is 1 by I x x and A is 1 by I y y. But if you write the Hamiltonian itself as Hc into a centimeter inverse dependent operator H prime, then you have a Hc. Therefore, that Hc can be used to divide. So, what you will have is H by 8 pi squared. I will not be there, I is already here. Pi squared C. Okay. And then this B H by 8 pi squared, let me write this, maybe it is better to rewrite this not in this form. Let me erase this, maybe this is not the right way of doing it. Let us write this down as H by 8 pi squared C times 1 by I x x j squared minus j z squared operator plus 1 by I z z j z squared operator, and then rewrite the constants A and B as, now this is in wave number unit dimension, the Hamiltonian. And so, what you have is, now you can write this as B j squared minus j z squared plus A minus B j z squared. Okay. So, this is the symmetric top Hamiltonian, and you remember that the eigenfunctions psi j k, which are the eigenfunctions of the Hamiltonian psi j k, is equal to E. Now, depending on the two quantities j and k, psi j k. For a diatomic molecule, the energy did not depend on k, because the diatomic molecular Hamiltonian had only B j squared as the operator, and that had an eigenvalue B j into j plus 1. Okay. For a polyatomic molecule, now you have a j z square is also part of the Hamiltonian, and the k is such that the eigenfunctions that you have psi j k or eigenfunctions of the operator j z, psi j k gives you k times psi j k. J squared psi j k gives you j into j plus 1 psi j k independent of k. These come from the, these are derived from the quantum mechanics of the rotor. Therefore, you can see that the k taking on the values 0, plus minus 1, plus minus 2, all the way up to plus minus j, ensures that the energy E j is no longer the same for all the 2 j plus 1 k values, but the energy E j will now be specified by j with the k. Let me put the k here instead of 0, and this energy for k is equal to 0 is non-degenerate. And for any other value of k, irrespective of whether k is plus k or minus k, you will see that the k non-zero, it is doubly degenerate. Okay. Therefore, if you go back and write this Hamiltonian in wave number units as as B j square plus A minus B j z squared, then H prime acting on the wave function psi j k will be B j squared operator acting on psi j k plus a minus b the j z square operating on the wave function psi j k, and therefore you will get the answer b j into j plus 1 plus a minus b k squared times psi j k. Therefore, this is still the eigenvalue and eigenfunction. Therefore, the Hamiltonian acting on a symmetric top eigenfunction now has eigenvalues which are functions of k, whereas for a diatomic molecule we had only this term. The A B difference was not there because you remember one of the moments of inertia for a diatomic molecule was 0 and the other two moments were the same. Therefore, we had only one term in the rotational Hamiltonian b j squared. Therefore, b j into j plus 1, that is what we had. Whereas in the case of a symmetric top we have a minus b k square, and now you can see why plus or minus k does not change things. Therefore, the wave function psi j k and the wave function psi j minus k both will have the same eigenvalue because it depends on k squared. Okay. That is why it is doubly degenerate. When k is 0, obviously there is only one energy b j into j plus 1. Now you recall A is inversely proportional to I z z and b is inversely proportional to I x x. Therefore, you can see that if I x x is less than I z z, then b is greater than A. If I x x is greater than I z z, then 1 by I x x is smaller than A, therefore, b is less than A. These are the two cases that we associate with prolate and oblate symmetric tops, and therefore, you see that the spectrum of the symmetric top Hamiltonian now dependent on the k square as well as the sign of the difference A minus B. So, let us quickly see the spectral features of a symmetric top. First, we will write down the energy levels. Therefore, E j comma 0 is b j into j plus 1, E j comma plus minus 1 is b j into j plus 1 plus a minus b, and E j plus minus 2 is b j into j plus 1 plus 4 a minus b k squared, and so on. Okay. Therefore, if you take say j is equal to 1, you have got two energy levels, k is equal to 0 corresponding to j is equal to 1 is b j into j plus 1, this gives you 2b, and if k is equal to plus minus 1, the energy is 2b plus a minus b, it is a plus b. This is the energy level, two energy levels for the symmetric top. Very quickly you can see that this is how the spectral features are present. Okay. So, we will see that in this play, animated play. You can see that the energy levels are such that you see for k is equal to 0, of course j is 0, this is the 0 energy level, and when j is 1 you have got k is equal to 0, that is a 2b, and when k is plus minus 1 you will have the other energy level a plus b. For j is equal to 2 you will have three energy levels, 2 0, 2 plus minus 1 and then 2 plus minus 2, one more level. And likewise for all the others, for j is equal to 3 you will see 4 energy levels, namely 3 0, 3 plus minus 1, 3 plus minus 2, 3 plus minus 3. See one more energy level. And the nice thing is that these are the only allowed transitions for the symmetric top, and there is nothing other than 2b, 4b, 6b, 8b as the energy differences. Therefore, the spectrum of a symmetric top is identical to the spectrum of a diatomic molecule. Therefore, by looking at the spectrum you cannot say anything about it. this is the particular case. And in this case, of course, I have chosen A greater than B, and if you do A less than B, a similar picture can be arrived at. So symmetric top molecules are very important in having the molecular shapes and other molecular geometries determined through the microwave spectroscopy. A lot more can be said about them, and of course the asymmetric top has even richer spectrum than this, with all the 3 moments of inertia being the same, but those things will form the course in a slightly more advanced course on rotational and vibrational spectroscopy. I will say those things. At this point, let us come to the end of this course and realize that with the elementary introduction to quantum chemistry and the model problems, we have looked at 2 or 3 elementary branches of spectroscopy, and we have carried out some investigations. I wish you all the best. The next set of lectures for the end of this course will solve some of the problems, but they will be helpful for you in solving the assignments. And my hope that you have enjoyed these lecture series so far, and that you will come back to understanding spectroscopy and quantum mechanics in more details. I wish you all the best. Thank you very much for your patience to be with me for all these 36 or 38 lectures. I wish every one of you a very, very bright academic or industry or whatever profession that you want to choose. I wish you all the best. Thank you.